We've talked about the geometric random variable, where we perform identical trials until we get our first success. Now let's generalize that and perform identical trials until we get our kth success. Doing this is called a negative binomial random variable. So let's perform identical independent Bernoulli trials. So that means each trial is either a success or a failure. I'll write this over there. Probability of success equals P. Probability of failure is 1 minus P. If X equals the number of trials to get the first success, then we write X is a geometric random variable with parameter P. So now let's suppose X equals the number of trials to get the kth success. Then we'll write X is a negative binomial random variable with parameters K and P. K, the number of successes we want to see. And P, the probability of success on any trial. So with this notation, a negative binomial random variable with parameters 1 and P means that we want one success. So that's the same thing as a geometric random variable with parameter P. Now I claim that the probability that it takes n trials to get those k successes, so if X is a negative binomial random variable with parameters K and P, then the probability that it takes n trials to get those k successes is n minus 1 choose k minus 1, p to the k, 1 minus p to the n minus k. Proof. We have, so the n minus 1 choose k minus 1 means I'll write it again. I'm going to write it a little differently. I'll write it n minus 1 choose k minus 1 times 1 means first of all, the 1 is we'll choose the nth trial to be success, and then k minus 1 of the previous trials, k minus 1 of the n minus 1 previous trials to be successes. And then p to the k, 1 minus p to the n minus k is sort of obvious. P to the k is the probability of getting those k successes, and 1 minus p to the k, 1 minus p to the n minus k is the probability of getting the other n minus k failures. So that's where that expression comes from. Now I mentioned a connection to the geometric random variable, that is the negative binomial random variable, where we're looking for one success is just a geometric random variable, because that's also a situation where we're looking for one success. There's another connection that I want to point out though. So let's say we have k geometric random variables. Let y1 through yk be independent geometric random variables. So yi is geometric with probability p. Then if we add these together, then that's just a negative binomial random variable with parameters k and p. So every negative binomial random variable is I'm claiming is the sum of geometric random variables. And the reason is that to get k successes, we wait for the first, then we wait for the second, then we wait for the third, and finally we wait for the kth. And each time we're waiting for one success. That is that each one of those waiting times is just a geometric random variable. Now, writing the negative binomial random variable as the sum of k geometrics makes it easy to figure out what the expected value and variance are. So if x is a negative binomial random variable with parameters k, we want k successes, probability of p having a success on each trial. We have the expected value of x is k over p, and the variance of x is k times 1 minus p over p squared. The reason for this is, so let's let y1 through yk be geometric random variables with parameter p. Let them be independent. Then x is the sum of these, and expected value of x is the sum of the expected values of these. The expected value of each one is 1 over p. And we've got k of them, so that's k over p. Now by independence, we can say that the variance of x is the sum of the variances too. Now the variance of a geometric random variable is 1 minus p over p squared. So 1 minus p over p squared k times is k times 1 minus p over p squared. So those formulas are pretty easy. Just k times the formulas that we know for the geometric random variable. So let's do an example. Let's continue the example that we used for the geometric random variable. So we said we would roll a pair of dice until rolling 7. So we stopped with the geometric experiment when we got 7 for the first time. But now let's stop when we roll it for the third time. So we want 3 successes. Let's let x be the number of rolls required. So then x is a negative binomial random variable where we want 3 successes, and the probability of each success is 1/6, because there's 6 ways to roll a 7, and there's 36 ways to roll dice. 6 over 36 is 1/6. So how many rolls would we expect? Well, we said with the geometric random variable that we expect 6 rolls to get our first 7. So if we're going to do that 3 times, I guess we expect 18. So 3 times 1 over 1/6. 3 times 6 is 18. So let's look at the probability that it takes exactly 18 rolls to get those 3 7s. So we want 2 successes in the first 17 rolls and then 1 success on the 18th roll. And probability of success is 1/6, so that's 3 times, and then probability of failure is 5/6, so that is 15 times. 5/6 to the 15th. So I put this in a calculator, and it turned out to be about 0.041. And that seems a little bit low to me intuitively, because a number that we would expect to see there. If we're going to try and roll 7 3 times, and it takes about 6 times to get each 7, we'd expect it to take 18. So I expected a higher probability there. So let's compute another one. The probability that it takes 12 rolls. So that's shorter than what we would expect. I would think maybe that's a smaller probability. This is already pretty small though. So we want 2 successes in the first 11 tries and then a success on the 12th try. 3 6s. So, sorry, 3 times 1/6, 3 successes. And then how many failures? I guess 9 failures for a total of 12 rolls. So I plugged this into a calculator and I got 0.05. So it's even bigger. But still really small. 5% seems like a small probability. So let's see why this might be. Why are these probabilities so small? So I computed lots of probabilities. Actually, I looked on the internet to do these computations. And it turns out that for any fixed k, the probability that it takes exactly k rolls doesn't get very high. It only gets to about 0.05. This is as big as it gets. So if we graph probabilities on this axis, and then number of trials on this axis, then the numbers I found were for 5, it's about 0.02. For 10, it's about 0.045. For 12, we said it goes up to 0.5. For 15, it's 0.048. For 20, it is 0.035, roughly. For 25, it is roughly 0.022. For 30, it's about 0.015. So roughly the probabilities make this curve here. And it flattened out. It took a long time to get down very close to the x-axis. So we can see that between 5 trials and 30 trials, we've got a significant amount of the probability. Between 5 and 30, there's about 25 numbers. And those 25 numbers are sharing a total probability of less than 1. It's not 1 because there's a little bit of probability here and there's a little more probability there past 30. But if we have 25 different numbers sharing a probability of 1, that means that each one of them on average can't be any bigger than 1 over 25, which is 0.04. So that's why we don't see things getting too much higher than 0.04. In fact, it seems a lot of them are less than 0.04, but that's because they're not adding up to 1, they're adding up to less than 1, because we've got some probability here and some probability there that goes very far to the right. So this suggests to me that the observations, if we were to do this experiment over and over and get 18 and 15 and 22 and 12 and other numbers, they'd be sort of spread out. We wouldn't have all of our observations being right at 18 or right at 12 or 15 in this range. So it suggests to me that maybe the variance is kind of large. So let's compute the variance. So the variance we said is k times 1 minus p over p squared. K is 3 because we wanted 3 successes. 1 minus p is 5/6. That's the failure probability. And then p squared is 1/6 squared. So what do we have? 3 times 5 over 6 divided by 1 over 6 squared. 6 squared over 6 is 6. So 3 times 30 equals 90. Okay, so maybe that is kind of a large variance. So the number of observations which are very close to the mean maybe isn't that much, which would be consistent with the probability of being near the mean of being kind of low. All right, now let's look at another variation on the negative binomial random variable. That's a very related question that we could answer with negative binomial random variables. Let's define a random variable capital V. Let's let this be the number of trials required to see k successes or k failures whichever comes first. So what's the probability it'll take n trials to see either the kth success or the kth failure, whichever comes first? I claim that the probability that V equals N, we want K successes or K failures, the probability that V equals N. Oh, I need to define some random variables first. Well, it's the probability that X equals N plus the probability that Y equals N, where X is the number of trials to the kth success, and Y equals the number of trials to the kth failure. So I'm thinking of this as maybe two people are playing some kind of match, and the first one to win K games wins the match. So K successes is going to be like player 1 wins K first, and K failures is going to be player K wins K times first. So the first player to win K games wins the match. We have two players. The probability player 1 wins any game is P, and the probability that player 2 wins any game is 1 minus P. That's just how I'm thinking of it. So why would it be the sum of these two probabilities? Well, each of these says the probability that player 1 wins K games takes N tries. So the nth game is a victory for player 1. And here this says that the nth game is a victory for player 2. So those are mutually exclusive because they can't both win the nth game. So we have X equals N. Player 1 wins kth game on nth try, and Y equals N. Player 2 wins kth game on the nth try. These are mutually exclusive. They can't both happen. So that proves the sum. And, well, why don't we find a formula for it? So for player 1 to win the kth game, in the nth game is the kth victory, is we have n minus 1 choose k minus 1. So there's k minus 1 victories before the last one, and then a victory on that nth. P to the k victories for P for player 1, and 1 minus P to the n minus k. N minus k victories for player 2. And then for player 2 to win, also we have k minus 1 victories for player 2 in the first n minus 1, and then a victory on the nth try. So now P is player 2 losing, player 1 winning. So player 1 wins n minus k of them, and player 2 wins k of them. The end.